Um, I'm going to kind of date myself. It was 50 years ago, next month, that I got my first exposure to the Navajo sandstone. I grew up in Wilmington, Delaware area in the Washington, D.C. suburbs, and I'd never seen much of Utah before until I came out to Brigham Young University to go to college. And when I decided to major in geology, it was 50 years ago. And our professor of physical geology, the late great Ken Hamlin, took us on a 4-day field trip that went all over southern Utah and to the Grand Canyon. And this is where I first saw the Navajo sandstone. Dr. Hamlin explained to us that the Navajo represented a depositional environment of a great sand sea or great dune environment like we find in the Sahara Desert. He also explained to us what crossbedding was, and that by looking at crossbedding and making measurements, we could determine which way the wind was blowing at the time that the sand dunes were deposited. And so on our field trip, wherever we stopped at the Navajo, and there were many stops, we got out and we tried to make crude measurements of the Navajo and the crossbedding, and then plot them on a map. And sure enough, we saw that the wind direction was generally coming from the north, out of, not surprisingly, Wyoming. And so this was just a great way to see the Navajo. And again, as I said, it's my favorite formation, and I've been trying to learn about it for the last 50 years. To that effect, I'd like to thank everybody that's helped me learn the Navajo over the years. I like to say that I know good stuff when I steal it, and I've stolen a lot of stuff from all these people to put this talk together, and I really thank them for their efforts as well, their friends and colleagues over the many years. I like to say that over the 50 years, the Navajo is actually, the canyons that I first saw are deeper, and the outcrops are back farther than they were. But you can't really think of the Navajo without thinking of the exposures that we find in Zion National Park in the southwestern part of the state. Specifically, some of the more iconic features include what's called the Great White Throne. And I know some of you are very familiar with the Navajo, others know a little bit about the Navajo, and maybe some that are tuning in know very little at all about the Navajo. So I'm really going to kind of try to cover a little bit of it. So some of this you'll know, some of you won't know some of this. Another very iconic feature within Zion National Park is called Checkerboard Mesa. The Checkerboard Mesa is a combination, it's a butte that's a combination of both joining and crossbedded sandstone that Dr. Hamlin first showed us. Not too far to the west is my favorite state park called Snow Canyon State Park. Here we see fantastic exposures of crossbedding in the Navajo sandstone, and the valley there is, and some of the Navajo is filled with Pleistocene age lava flows. So it really makes those crossbedded sandstones jump right out at you. Moving a little bit farther to the east in Capitol Reef National Park, Navajo Dome is formed by the Navajo sandstone. The Navajo sandstone also forms the flanks of major laramide uplifts throughout southern Utah. This is the east flank of the San Rafael Swell in the east central part of the state. And that big ridge, or reef as they call it, is composed primarily of Navajo sandstone, as well as many of the other uplifts throughout the region. The Navajo sandstone is also a site of hanging valleys, and these can be places where during flash floods or significant rain, you'll find spectacular waterfalls such as Calf Creek Falls here, which flows all the time essentially. This is in the Grand Staircase National Monument in south central Utah. The Navajo also forms beautiful alcoves and hanging gardens where it's exposed in southern Utah. Pools of, we call them, often called water pockets or potholes, on top of the Navajo are developed, and these are the sites of just teeming with life. The Navajo also forms very large arches. This is Corona Arch, and maybe after the last year we need to change the name of Corona Arch. This is near Moab. And Corona Arch is about 110, is the height of 110 feet and a width or a span of 110 feet. It's also a site of people bungee jumping, and there was a tragedy a few years ago where they miscalculated the bungee cord and he didn't quite make it, made it too far to the bottom. But Navajo creates lots of arches throughout southern Utah. Of course, one of the largest natural bridges in the world is Rainbow Bridge near Lake Powell. It formed in the Navajo. Rainbow Bridge is 246 feet high and 234 feet, has a 234-foot span. You can tell by the age of this photograph that I took back in the late 1990s that the lake was actually underneath the bridge, of concern at that time. However, now you have to walk almost a mile to get there. The Navajo also forms the Wave in Paria Canyon with these amazing crossbeds on the Utah border with Arizona. It's actually just over the border in Arizona, and a special permit is required to get to that site. There's some really strange things that are associated with the Navajo. These are these iron concretions or Moki marbles that weather out of the Navajo. And I'll talk a little bit more detail about them later on in the presentation. Bend Canyon Dam that forms Lake Powell is built into the Navajo Sandstone right on the border in Arizona, just over the Utah border. Now, for those of you who are not afraid of heights, and I have kind of a vertical limit. The most terrifying hike in Utah is Angel's Landing hike in Zion National Park, where literally you have to hold onto a chain that separates you from cliffs on both sides that drop almost 2,000 feet down. I have never done this, and never probably will. However, I have done this. The Slick Rock Trail near Moab is a very popular bicycle trail where you're riding on top of the Navajo. That is the Colorado River in the distance there. And I did this a number of years ago, and of course I crashed about 2 or 3 times in the process of going the Slick Rock Trail on top of the Navajo. The Navajo is not without its hazards. There are surface fracturing in the Navajo that cause exfoliation or the spalling off of great sheets of rock that come crashing down, as seen in this example taken in 1983 at the Rainbow Bridge courtesy dock. So I'm going to talk about, again, some of the general characteristics of the Navajo, the paleogeography and environments, the stratigraphy, particularly the J1 unconformity, the sedimentary structures, petrography, the facies, both the dune and interdune, some of these strange and wondrous features, I like to call them, that we've seen already, such as the Moki marbles and such. And then the Navajo as itself where it serves as a reservoir for hydrocarbons and natural CO2. It's an aquifer for disposal produced water and culinary water, and then its potential for carbon sequestration. This is a view from looking into Eagle Canyon on the west flank of the San Rafael Swell in east central Utah. The outcrops are typical of the Navajo, where they display rounded cliffs, domes, and knobs that epitomize what is called slick rock country. The Navajo ranges in thickness from 150 to 2,300 feet. And the sandstone beds are very friable. They're composed of clean, this is kind of a mouthful, clean, fine to medium grain sandstone. It's sand grains. They're sub-rounded to rounded or subangular. It's moderately to well sorted, and the grains are often frosted, typical of what you might expect in an Aeolian environment. It also contains minor amounts of feldspar and some scattered heavy mineral grains. However, the most iconic feature, distinguishing feature of the Navajo, as previously mentioned, is indeed the spectacular crossbeds seen here in Buckskin Gulch in south central Utah. The source of the sand within the Navajo comes all the way from the east, based on work by Dickerson, coming from the Appalachian region, and then transported in west-flowing streams laden with sand north of Utah, and then blown south to form this large erg system in early Jurassic time. Utah at this time also had an arid climate and was about around 15 degrees north of the equator. The Navajo and its age equivalent formation, age equivalent rocks, such as the Nugget Sandstone in Wyoming and the Aztec in Arizona and part of Nevada, were deposited in this extensive erg, which existed from Wyoming to Arizona, as I mentioned. Now I plotted on here the wind direction as determined by Pickard in 1975 on top of this Blakey-Rainey paleogeographic map. And of course, it shows, similar to our crude map that I made as a first-year student in geology, that the wind was coming out of the north to northwest. I've also spotted the oil field, Covenant oil field, that was discovered in 2004 in central Utah thrust belt that I'll be discussing more later on in the presentation. Now, we don't think of the Navajo without thinking of modern analogs, such as the giant dunes that are within the Sahara Desert, as my great professor Hamlin told us about. The dunes there, as well as in the Navajo time, were large, sometimes with widths up to 2,200 feet thick, but also they might have been small, straight crested to sinuous, coalescing transverse barkanoid ridges, as suggested by the big crossbeds that are so prominent in the Navajo. You don't have to go very far, and you don't have to go all the way to the Sahara Desert to see modern analogs. And this is Little Sahara Recreation Area in western Utah. And this is an aerial photo taken by Hamlin in his 2006 book. And I like to show this picture because you see a lot of things in it. You can see a wide variety of dune types. There's actually a star dune. There's low, good old scam. Got my timer on here. Excuse me. There are low parabolic dunes with trailing arms. There are barken dunes. There's transverse dunes. But if you look from the right side, panning across the image here, you'll see on the right that the dunes are very closely spaced together. As you move across through the center of the photograph, they're more and more separated with interdune areas in between. And then as you get farther and farther to the left side, you'll see more and more areas of interdune deposits. And this just gives you an idea of, if you imagine a reservoir or an aquifer, the heterogeneity of the Navajo or the dune environments that can change so rapidly over a relatively short distance. This is really just a couple of miles that you're seeing in this image. Again, we see dunes will tend to be stacked as they were deposited. And here we see in Buckhorn Wash in the San Rafael Swell, 3 different sets of dunes dominated by the large cross stratification. Again, going back to modern analogs in the Sahara, it wouldn't be thinking of the Sahara without thinking of oases. In this case, this example is shown in Libya, where we have a freshwater pond surrounded by vegetation, but very close to large dunes nearby. And we see the same thing in other places as well. This is in the Alaskan area of the Gobi Desert in China. And here we see gigantic dunes, just very similar to probably what formed in the Navajo. But note in between the dunes are these fairly large ponds. I'll try to point them out here, some of them that exist here. And this is because probably in this area, there was a high water table that allows the ponds to develop in between large dunes. This is the Lincoln's Marahanese, pardon my Portuguese, National Park on the northeastern coast of Brazil. And here we see literally hundreds of ponds in between elongate dunes. Again, because the water table is very shallow here near the surface, creating these ponds. And also note the green color that's associated with algae that's forming within these interdune ponds here on the coastal dune field along Brazil. Well, if you go to, again, you're going to gather that Lake Powell is one of my favorite places, and we were forced to do our work. We created a lake log, so if anybody ever goes down there, cruising around Lake Powell. We've produced a geologic lake log in 2000. Takes you from one end of the lake to the other, and the National Park Service provided us a boat. This is me 22 years ago, sitting on a limestone deposit within the Navajo Sandstone. I would now be sitting on a cliff about 200 feet above the water. In 1998, the lake was at near full pool, and now we're about 1/3 full pool. So this deposit would be way up high. So within the Navajo, we see at Lake Powell and many other places in southern Utah, we see many thin-bedded lenticular limestone beds that we interpret as interdune oasis deposits. They're generally thin, 5 to 10 feet thick, horizontally bedded limestone, and can come and go. The limestone beds have often yielded fossil plants, such as actually tree trunks and invertebrate fossils. The fresh groundwater had to exist at a fairly shallow depth and persist for a prolonged period of time, perhaps as many as several thousand years, to allow the lake or ponds to develop these limestone deposits of this thickness. The other thing that they show, many of the limestone beds contain algal laminae, or microbialites, most likely created by cyanobacterium. My friend Dave Eby has worked extensively with us on these and other deposits. As a matter of fact, we just published recently, just a few months ago, our study on microbialites in Utah, available for free at the Utah Geological Survey's website. So I have to throw a plug in for that. So we see these microbialites within these limestone beds or these oasis deposits. And this is a Cross-Nichols thin section photomicrograph from one of these deposits around Lake Powell. And here we see almost a stromatolithic characteristics of the laminae. In this example, we see dark colored clots and pin-cushioned like patches of micrite that are surrounded by lighter color, partially dolomitized detrital sediments and small white quartz grains, presumably representing sand grains blown in by the wind from nearby dunes. The clotty nature, or the lumpy clots, are termed thrombolites, or this would be what we would classify as a thrombolite or thrombolytic microbialite deposit. These microbial structures are probably easily formed in a stressed environment that was intermediately desiccated. Again, think of the Brazilian example, or even in any of the other examples where we see that the salinity and stresses from the salinity will range from fresh water to hypersaline waters as these ponds come and go or dry up. In fact, some of the examples that we saw, again, unfortunately very high up now in the cliff faces around Lake Powell, we saw ripple marks topped by mud cracks and salt casts as these ponds changed and dried up. As I mentioned before, these things can be very thin and they pinch out rather rapidly. This is just one example. You can see it pinching out to the left in this example, but then fortunately you can go up a canyon, cruise up the canyon, and I projected the path of a canyon hypothetically here in this cartoon. And you can see how you would see these limestone deposits come and go as you cruise up a canyon, but you're probably looking at the same oasis deposit. Another thing that we've seen at Lake Powell are dinosaur tracks. And these tracks are found at a place called Tapestry Wall north of Bullfrog Marina. And now it's probably about 300 feet above the lake level. And there's about 14 tracks here of this three-toed theropod that represents the ichnogenus genus Eubrontes, which was presumably to be about a 20-foot long carnivore. We assume that it was tracking along in an interdune environment, heading towards an oasis to either get a drink of water or eat another dinosaur. Another thing that we have compared the Navajo to, or in terms of modern analogs, are wadis, or these dry channels that are found in, particularly in the Middle East, such as this example from Egypt, and other examples from Israel and the United Arab Emirates. We find them again in the Navajo sandstone, represented by this brown deposit that's below this cross-bedded sandstone that I'm sitting on. Again, one of my favorite areas at Lake Powell is cruising up towards Rainbow Bridge. And a lot of people are just going to gawk at the bridge, but if you ever go there, you'll know several of these fairly distinct channel deposits on the side of the cliff faces. We think these represent wadi deposits, or wadi channels that existed and that went through the various dunes. Fortunately, there was a big chunk that was down right actually by Rainbow Bridge that we could examine in detail. We kind of call this a pudding stone. It consists of fragments of rounded sandstone and clast and gray subangular to subrounded dolomitic limestone clast. These clasts can be from just little small pebbles to small boulder size that make up this rock, and they are bound in a matrix of medium to coarse grained sandstone cemented with iron-bearing quartz. This block, you can see some horizontal stratification and some small scale crossbeds. It also contains rip-up clasts, particularly down here in the bottom part of it, that are imbricated and inclined in a downstream direction. Going back to my similar cartoon of the path of the modern canyon here, as we're cruising towards the Rainbow Bridge, we would see several of these channels cutting through the dune deposits. Let's turn our attention now to the stratigraphy of the Navajo itself and the J1 unconformity that separates it from the overlying formations. When we went with Dr. Hammond on that great trip 50 years ago, we looked at the Grand Staircase, which are the sequence of rocks and cliffs that form northward from the Grand Canyon. And this is one of his aerial shots. We see here the Chocolate Cliffs, composed of the Triassic Moenkopi Formation, the Vermilion Cliffs of the Jurassic Muana Formation, and then the dominant White Cliffs, composed of the Navajo Sandstone, with the pink cliffs on the skyline representing the Tertiary Clarion Formation that forms Bryce Canyon. But the ones that really stand out to you are the White Cliffs, made up of the Navajo Sandstone. The Navajo Sandstone I mentioned is equivalent stratigraphically in part to the Nugget Sandstone to the north in Wyoming, southwestern Wyoming, and to the Aztec to the south in Arizona and Nevada. Here, near the east entrance of Zion National Park, we see the Navajo Sandstone is capped by what's called the Temple Cap Formation. The Temple Cap Formation is also in part Aeolian, specifically the White Throne member, which represent coastal dunes. And the bottom member is the Sinawava member, which are coastal tidal flat deposits. And the iron mudstones within those are what stains the Navajo red throughout much of Zion National Park. The Temple Cap is Middle Jurassic age, and it's separated from the Lower Jurassic Navajo by the J1 unconformity. Sorry, I'm getting a drink of water. The Temple Cap is not present everywhere. This is, again, in the San Rafael Swell, in the Eagle Canyon area that I showed earlier. And here the Temple Cap's not present, but the Navajo is capped by the Middle Jurassic Carmel Formation, again separated by the J1 unconformity. The J1 unconformity is a major regional unconformity based on outcrop work, regional well correlations in petrography. My friends and colleagues, Doug Sprinkle and Bart Qualis and others and Helmut Doling have been studying for many years. There's a time gap of 10 million years between the early Jurassic and Middle Jurassic, determined by radiometric age dating from ashfall beds within the Carmel and Temple Cap and polymorph assemblages. The thickness of the overlying Temple Cap varies from 0 to 200 feet due to deposition on a paleotopographic surface developed by the J1 on top of the Navajo. I'll show you some examples of that. Down again by my favorite area, Lake Powell, The Navajo is overlain by the Page Sandstone, again separated by the J1 unconformity. And you can see in this diagram how the thickness of the page varies as the J1 on top of that topographic surface on top of the Navajo changes. And again, here at Dangling Marina in the middle part of Lake Powell, we can see that specifically where the J1 is present, and then the page thins to basically essentially goes away on that as an undulating topographic surface on top of the Navajo, and then it's overlain by the Carmel in the middle. Here in the Henry Mountain Basin area of South Central Utah, we see, again, the Temple Cap is present with that topographic surface on the J1 unconformity separating it from the Navajo, and how that thickness changes in the Temple Cap because of that changing topographic relief. This is a regional cross-section that Doug Sprinkle put together and others. And here in the middle is the 17-3 well from Wolverine's Covenant Field in the central Utah thrust belt. To the west, the Temple Cap is much thicker, and it changes to being very thin at the east. But within this well, originally we thought that the entire section of core was all Navajo when the field was first discovered. However, we encountered what we thought was a Sinawava member of the Temple Cap, or Sinawava we thought was part of Navajo. We encountered glauconite as well as marine polyomorphs. So we changed the interpretation to being representing the Temple Cap Formation separated by the J1 in this core. And both the Temple Cap, by the way, and the Navajo are productive within the field. Okay, so the unconformity, J1 unconformity and outcrop cores, we see a bunch of several characteristics, particularly a lag of pebble to cobble-sized chert fragments. There's breccia zones and large polygon shrinkage cracks, carbonate nodules and bioturbidation. There's bleaching zones, and the Navajo is slightly more enriched in barium and gallium and less variable in iron oxide than the overlying Temple Cap, based on the work, statistical analysis of XRF and elemental data done by Stephen Phillips and Tom Morris of Brigham Young University. So in outcrop, we see in these examples, on the left, we see these angular chert granules in the Black Canyon area on the east flank of the San Rafael Swell at the J1 unconformity, and some large shrinkage cracks shown here on the right at Steinecker Reservoir State Park in eastern Utah. This is a core from that 17-3 well in Covenant Field, and on the one on the left, we see a gravel lag that may represent the J1 unconformity. We also see these bleaching zones as well, where iron has been leached out or so forth, that may be near or at the J1 unconformity. We are still arguing about that. After Covenant was discovered in 2004 in the central Utah thrust belt, my colleagues at BYU and the Utah Geological Survey began a project to study the outcrop examples as a reservoir analog of the Navajo to what we anticipated would be a whole series of new fields discovered in the central Utah thrust belt. To date, only one has been discovered since, a small field called Providence that was discovered in 2008, just north, a few miles north of Covenant Field. Nevertheless, the outcrop study I think is very useful, and we just recently published it as well in 2020, that it's useful for all the many other aspects of the Navajo that I'll be talking about later. Our study area was in the Eagle Canyon area that I showed in an overview picture just off of the Interstate I-70 along the west flank of the swell. In our study, we identified a number of subfacies within the Aeolian deposits of the Navajo, both dune and interdune. The dune ones include what we call large trough cross stratification, or LTC, small trough cross stratified, or STC, reworked Aeolian, RWE, and then interdunes for wavy algal mat, or WAM, sandy algal mat, or SAM, and evolving interdune, IED. So in cross-section, the typical characteristics of the LTC, the large ones, are the crossbeds are large, 50 feet thick or more, thick-bedded, fine to medium grain. They're well sorted, and have great reservoir quality and outcrop, 27% porosity on average and over 100 millidarcies. The small or STC crossbeds are thin, 3 feet or so, thin to medium bedded, fine to medium grain. They're moderately to poorly sorted. They have gradational contacts, but they can have good porosity, but generally have lower permeability and occur mostly in the lower Navajo. The reworked eolian can be massive and contorted, perhaps because we think, again, that high water table that existed throughout much of the Navajo region would have caused saturation and a lot of the crossbedding to be essentially destroyed. It's not very laterally extensive. They can be thin bedded and fine grained, moderately sorted, and generally have a little bit poorer reservoir quality than the crossbedding. In terms of the inner dunes, we see these wavy algal mat or WAM are composed of that stromatolitic wavy laminate, very similar to what we saw earlier in the Lake Powell area. There's desiccation features, again, what we saw in outcrop down there, disrupted bedding. They tend to be very fine grained. We did not find any fossils, but they are very laterally extensive. However, the reservoir properties are very low, and they would actually serve as a barrier or baffle to fluid flow. The SAM or sandy algal mats are thin to planar laminate as well, but they're not very laterally extensive, 3 to 6 feet. Again, very fine grain and similar in terms of low permeability and probably more or less a barrier or baffle to fluid flow. And the evolving interdunes tend to be this, again, massive undulating contacts, very fine grain, again, low permeability, representing a barrier or baffle to fluid flow. Now, one of my favorite aspects of the Navajo are what I like to call the strange and wondrous features. Here I see some examples that Margie Chan from the University of Utah has been studying near Moab. And these are these iron manganese rich injectites in the upper part of the Navajo. And the staining away from the core of the injectites indicate fluid direction. And perhaps on the field trip, you'll get to see some of these in the October RMAG field trip. Another thing is, that I showed earlier are these beautiful alcoves and hanging gardens that are so common throughout the Navajo, but they're especially great to see while cruising around on Lake Powell. The alcoves form where groundwater percolating down through the pores in the sandstone encounter low permeability bed, such as our oasis deposit or an interdune boundary. Such beds have a higher silt content that then impedes the continued flow downward. And so that the groundwater then flows, is restricted, and then the water moves horizontally along the less resistant flow path and exits at the rock face, forming a seep or spring. In the process, the water dissolves and removes cementing minerals in the sandstone, causing the rocks there to weaken relative to the rocks elsewhere in the cliff, as shown in this cartoon here. The process of weathering and erosion on the weakened rock and eventually forms a recess or alcove in the cliff face. The increased water and shade are ideal for a variety of plants, which further aid the breakdown of the rock. So they get bigger, these alcoves get bigger and bigger over time. And they're a great place to camp under, but I get very nervous under them after a while. The wet surfaces are often covered with mats of various kinds of algae, ferns such as maidenhair and bracken, grasses and sedges. And again, one of the more unique features, I showed a picture of these earlier in the presentation, are these iron concretions, which are also called Moki marbles or Navajo cherries, that weather out of the Navajo. And they can be found prolifically in various areas, such as this one here in the Grand Staircase Escalante National Park, or in Snow Canyon State Park, and many other areas around Lake Powell. It's always a temptation to collect these, but it is illegal. These features consist of a well-cemented limonite or iron shell or hematitic iron shell around a friable sandstone core. Most are these spherical shapes, but they can be saucer shaped, and they range in size from little pea size things or BB size all the way up. I've seen them as big as baseballs from the grand staircase. They most likely formed when groundwater that might have been acidic or hydrocarbon bearing or carbon dioxide bearing removed the hematite within the Navajo and then precipitated them around small impurity, precipitated the iron around a small impurity in the rock. And then it grows as more iron is precipitated, forming the concretion. The iron also can migrate outward towards the precipitation front, leaving the core of the concretion weakly cemented and forming the dense shell around the softer sandstone center. If you look at the picture on the right, these are similar sphericals that were discovered by the rover Opportunity in 2004 on Mars. And they are also composed of hematite and provide further evidence of water in Mars's ancient past. And these are been called blueberries. Another unique feature or oddity about the Navajo is soft sediment deformation. Soft sediment deformation, again, we've mentioned the fact that we think the water table was high, and so this is likely one of the reasons that soft sediment deformation can be very common, destroying any kind of cross beds. And here's one of the most weirder of examples I've ever seen. It's called the Elves Toe in Capitol Reef National Park, and the arrow at the bottom is pointing to a person, just to give you a scale of this feature. Also in Capitol Reef National Park, right along Highway 24, when you cross through there, you'll pass some great examples of the soft sediment deformation here, and it's common throughout the Navajo, much of the southern part of the state. And this is an example on Antelope Island in Lake Powell of the soft sediment deformation in the Navajo. Another unusual and weird feature is this honeycomb weathering pattern, which is also called tophony, or some people like to just call them stone pecker holes instead of woodpecker holes. They form, this pattern of weathering occurs along cross beds or bed set boundaries. And the holes are created by differential weathering and case hardening where the groundwater has weakened the cement in the rock, commonly at small variations or imperfections. And once these are started, the voids provide space where water can accumulate and be protected from evaporation. That further weakens the cement in the rock and then promoted further growth, just like kind of a mini alcove formation. In case hardening, the mineral-laden water wicks towards the outer surface of the exposed face of the rock, where the water quickly evaporates, depositing the cement and strengthening the rock case. Finally, of these oddities or these wonderfully spectacular deformation bands or joint sets, in this case a conjugate set that's formed near a severe fault, which is a major north-south trending fault that goes through southern Utah all the way to the Grand Canyon. Well, onward to the other aspects of the Navajo. It's an oil reservoir. It's a reservoir for natural CO2. It serves as a disposal unit for produced water. It's an aquifer for culinary water. It has the potential for storing captured CO2. It's everything. As I mentioned earlier, there are two oil fields that have been discovered in the Navajo in the central Utah thrust belt, Covenant and Providence. Covenant, when it was discovered in 2004, made a big splash both here in Utah and actually made the cover of the Explorer magazine in 2005. Covenant is a relatively simple anticline bounded by a thrust fault. It trends in a north-south or northeast to southwest direction. And the arrow is pointing to a core I've already shown you. I'll show you some more examples from that core in a little bit in a minute or two. This is the cross section through Covenant Field with the Discovery Well. And you can see how the field's set up with a back thrust off of the Gunnison Salina thrust that creates an upper and lower Navajo. Only the upper Navajo, as well as the Temple Cap, are productive. The field has 34 active wells and has produced almost 27 million barrels of oil since it was discovered, but no gas, and 52 million barrels of water. It's still producing about 2,500 barrels of oil per day and over 14,000 barrels of water at an in-place reservoir of over 100 million barrels of oil estimated. And the ultimate recovery is estimated between 40 and 50%. So we're at about 27% at this point. The productive area is only about 1,600 acres, and the combined Navajo and Temple Cap pay thickness is over 400 feet thick, and both have about 12% porosity and upwards of over about 100 millidarcies with a strong water drive. And it's about essentially all quartz sand, as we'll see here in a second. We recognize some of the same facies that we saw in Outcrop 40 miles to the east. Here we see the LTC, or the large trough cross-stratified dune facies, and this makes up some of the best reservoir in the field. These cores are still smelling of hydrocarbons to this day, and they've been in our core center for almost 16 years. In this case, the porosity ranged from 13 to 15%, and the permeability is over 150 millidarcies. So this is some of the best reservoir rock in the field. We also recognize the small cross stratified, or STC, low angle or lower angle cross beds. And again, it is very good reservoir rock, and I don't really believe this permeability value is probably a fracture, but it is also reservoir rock in the field. We also saw reworked eolian as well as sandy algal mat in the cores. Both have relatively decent porosity, but poor permeability, representing either barrier or baffles to fluid flow, as we saw in our outcrop examples. Natural CO2 also is found in the Navajo at Farnham Dome field on the north end of the San Rafael Swell in central Utah. This is a generalized geologic map of the Farnham Dome field area, and there's a number of northeast to southwest trending normal faults, or faults through this area. This is a subsidiary structure on the north plunging nose of the San Rafael Swell, which is Laramide age. However, in cross-section, those surface faults die out in the anhydrite or gypsum beds within the Carmel Formation, which overlies the Navajo Sandstone. So the Navajo Sandstone is unfaulted. This is just a map of the Navajo Reservoir at Farnham Dome. The average depth of the well is only 1,800 feet, and the pay thickness is 40 feet with 12% porosity and over 100 millidarcies of permeability, typical of what we've seen in a lot of the Navajo outcrops and reservoirs. The gas composition is almost 99% CO2 with no hydrocarbons. The field has produced almost 5 BCF of gas, and initially the gas was transported via a pipeline to a nearby dry ice plant where it was used for food processing just to the west of the field. But more recently, the gas was compressed and trucked to the Uinta Basin to the north for hydraulic fracturing operations, which was generally suspended about 4 years when the gas prices crashed in 2014. Production first began in 1931, and the field is now currently shut in. The Navajo, of course, is also a produced water disposal unit, both at Covenant Field and at Drunkard's Wash Field, off to the northwest of the San Rafael Swell. Drunkard's Wash Field is a coal bed methane field and is the second largest gas field in Utah, producing out of coal beds in the Farron Sandstone member of the Upper Cretaceous Mancos Shale. There's nearly 600 wells in the field, but many of those are used for dewatering of the coal zones, which leads to the cumulative production of over 277 million barrels of produced water that need to be disposed of, or almost 360,000 barrels of water per month. And therefore, there are 10 wells that dispose that water into the Navajo Sandstone. Back to our cross-section of Covenant Field, there is a produced disposal well off to the west of the field. This well, when it was drilled, it was expected that it would encounter an upper and lower Navajo like the Discovery well, separated by a thrust splay. However, it only found the lower Navajo, and so it caused the structural interpretation to be reinterpreted such that there was a back thrust coming off the Gunnison Salina thrust to set up the field, rather than a splay that dips off to the west. So therefore, meanwhile, the production of water has increased greatly since 2010 here in Covenant Field, such that the cumulative water production is 52 million barrels and over 400,000 barrels of water, which are now disposed in that water well into the Navajo off to the west of the field. The Navajo serves as a crucial culinary water source and aquifer in the St. George area of southwestern Utah. St. George is a fairly affluent area of the state, and over 170,000 people live in the St. George area. This is a map showing where St. George is located, and of the aquifer classifications there, the Navajo is exposed, shown by the orange outline, and the pristine Class 1A aquifer is shown by the blue outline, both to the north and east of St. George, as well as the Class 2 drinking water aquifer shown in outlines in red. We look at north, south, and east-west structural cross-sections. You can see where the water table is present in the Navajo. So we have an extensive, relatively thick section of Navajo that serves as the aquifer, this very large and growing population of St. George and surrounding areas. Moving on to the southeasternmost part of the state, where the economy is very depressed and people live often in impoverished environments as part of the Navajo Nation. The Navajo serves as a crucial water source for the people that live there. This is a map of the Navajo Nation, and you can see here where the part of the Navajo that's in Utah, but it's a huge area, and the Navajo serves as an important aquifer for their culinary water needs as well as agriculture. This is just a cross-section in the Utah portion of the Navajo Nation, and we see that the water flow is generally through the Navajo and other sandstone formations, but the largest one is, of course, the Navajo. This aquifer sits on top of Greater Enneth Field, which is the largest oil field in Utah that has produced over 500 million barrels of oil out of the Pennsylvania Paradox Formation. So protecting that aquifer from potential leaks from wells or surface spills are critical to the people that live in that region. Finally, the Navajo serves as potential for storing carbon dioxide. The Utah Geological Survey, as well as many other organizations, University, Utah, and others, did an evaluation of the potential of the Navajo to serve as a potential storage unit for gas, carbon dioxide, from two power plants in central Utah, the Hunter and the Huntington Canyon coal-fired power plants along the west flank of the San Rafael Swell. In this study, we looked at the Navajo exposed around the flanks of this large, again, mentioned the Laramide age. Farnham Dome was up here, and Drunkard's Marshfield is here. And here's the axis of the Laramide age San Rafael Swell. The Navajo outcrops in this turquoise blue and part of the Glen Canyon group around the side. And this is a cross-section through the San Rafael Swell with the general western flank, and where the coal-fired power plants are located. We did reservoir modeling and outcrop studies to determine the possibility of storing the CO2 from the power plants as a supercritical fluid injected into the saline part of the Navajo at depth along that western flank. However, the project was not funded to the demonstration phase, and so it remains to be for the foreseeable future to occur. However, the Utah Geological Survey and others partners recently received funding or were awarded a grant to study the Navajo as a potential CO2 sequestration unit in the Iron Springs district of southwestern Utah, west of Cedar City, a growing population center as well, north of St. George. And here they're looking at the storage capacity, the risk and economic options for storing CO2 in the Navajo, as well as the Permian Kaibab Formation. Part of the study, they think that the Navajo may be capable of studying at least 50 million tons of CO2. And some of the planned activity are groundwater aquifer characterization and chronostratigraphy, analysis of the structural and tectonic history of the Navajo in that area, outcrop study of the Navajo, which makes me want to come out of retirement and join the group. They'll do 2D seismic and gravity surveys, and then examine both the historical and modern seismicity of the Navajo. Well, I made it through it. That is the Navajo, everything that I can think of, and then some. I appreciate the opportunity to speak today and tell you of my 50 years of looking at the Navajo, and hopefully I'll have more time to look at it again in the future in various capacities. And I'm happy to answer any questions at this time, or you can just email me at tomchidsey@gmail.com, and I'd be happy to see what I can do. Thank you.
Thank you, Tom. That was awesome. That was a really thorough presentation. Really enjoyed it. We're getting one question here coming in. What is the source of the oil at Covenant Field?
The source of the oil at Covenant Field, we did some, both Wolverine as well as the operator, which is Michigan-based Wolverine, and us, the Utah Geological Survey, Doug Sprinkle, and others here at the survey. I keep saying here at the survey, I'm no longer there, I'm finished. But, so we did biomarker analysis, and they did as well, and determined that it was most likely a carboniferous, perhaps most likely a Mississippian age source of perhaps unknown, maybe the Manning Canyon Shale, which is kind of a Mississippian Permian age unit. So unlike the Navajo or the Nugget that produces to the north in the Wyoming, northern Utah thrust belt out of the fields there like Pine View and Anschutz Ranch and so forth, Anschutz Ranch East, where the source is Cretaceous, subthrust Cretaceous, we think this is probably this Pennsylvanian age sourced oil or Mississippian age or sourced oil coming from either within the thrust plate itself to the west or subthrust to it.
Ron Parker's got a question here. Are there any interesting accessory mineral trends across the Navajo?
Well, I know that, again, Stephen Phillips did his thesis. He's a student of Tom Morris at Brigham Young University, and he did his thesis looking at the elemental data, particularly trying to identify that J1 unconformity, looking at the mineral or XRF and XRD analysis of what you might see across that. There are mineral differences between the Navajo and the Temple Cap Formation as well. Bart Koalas at BYU has also done a lot of work on zircons, particularly using them for age dating, but I have not done any specific analysis of the heavy minerals. Margie Tan has been doing a lot of work, as I showed, on the fluid flow and the deposition of the hematites and other iron-bearing, iron manganese minerals in the upper part of the Navajo, as well as she's done a lot of work on those Moki marbles or those concretions. Sorry, give me a drink.
There's a question from Greg here. Any production from the Navajo in the Uinta Basin?
Sorry, I didn't hear. In the Uinta Basin?
Any production from the Navajo in the Uinta Basin?
No, it's very deep there in the Navajo. We have done a study that we published just a couple in 2017, looking at the Navajo as, again, a potential produced water disposal unit within the Uinta Basin, but there is no production there in the basin. It would be way too deep, and only a well or two is actually penetrated, if I remember right. But we have looked at it and published on the potential as a produced water disposal unit in the basin.
There's one question here. It's kind of a long question.
Good to give my boys a chance to recover. Talk too much.
One slide showed very large scale leasing gang banding. I'm not sure which slide that was. that Lewis is referring to. Any thoughts regarding the process and timing of formation?
Most of that is fairly recent compared to the age of the soft sediment deformation. We think the soft sediment deformation in the Navajo is fairly kind of basically at the time of deposition versus a lot of these later features such as the Navajo, the concretions and some of the iron manganese deposits that we just mentioned. So I'm not quite sure. I'm trying to see where that might be. But again, that groundwater, maybe it's going to be in some of this stuff. That groundwater flow, I would imagine would be fairly new compared to the time of deposition. I've not studied that in detail. Most of my work has been in reservoir aquifer characterization. So I didn't see anything in particular there. I'm not quite sure. If they want to check, if this is recorded, maybe they can find it and then let me know what slide it was that
Sure, yeah.
That it was, and I can look at that a little more detail.
And then following up from Lewis, another question: what is the recognized distribution of reduced fluid related bleaching in the Navajo?
Yeah, again, I would refer Lewis to Margie Chan. She would be really the expert on this. This is what she's been working on extensively the last several years, and she is really Bill Perry, who is also at the University of Utah. Both of them have published a lot on that. They looked at a lot of the fluid migration and things like that, both in the covenant core as well as in outcrop. So I would defer to them because they are really, and look and maybe check some of their publications because that's what they've done a lot of work on. Still looking for that banding picture, but I'm not quite sure where it is.
Another question here is: any ideas as to why the Navajo is the host to the Arches?
Well, the Arches National Park, a lot of the arches are actually in the overlying Entrada sandstone. And so in the Navajo and similar formations, they're just prone to it because if you think of them as basically a piece of glass, when that glass shatters, then you have these joints. The joining is so prevalent, particularly in these areas. So you have joints, and then you have, if you have these alcoves that form, like I showed the example of the alcove, well, if an alcove forms along a joint, it might reach another joint on the other side of the alcove, and the next thing you know, that's how you form an arch. Some of the arches that are formed in there are called pothole arches, and that's where the pothole simply comes down from. I'm looking for my picture of the alcove formation, but so you imagine a pothole being that I showed earlier, very early in the presentation, the pothole, and if that pothole eventually wears down and encounters an alcove below, then that's how you get a pothole arch. And so you got wall arches, what are called wall arches that form along where a joint, you have a joint which has a fin essentially, and then an alcove forms on one side and an alcove forms on the other side, and then where they meet, then you get an arch, or you get a pothole arch forming the other way. So that makes it just that combination of the sandstone, the alcove formation, and the joining of these fractured, very brittle sandstone deposits result in so many arches.
There was another
quick and dirty version of that.
Another question was, did you say in the presentation that there was evidence of tree fossils associated with the Oasis deposits?
Yeah, there was a publication by the late William Stokes, and he identified trees, fossil trees, or impressions within some of the Oasis deposits. I myself have not seen those. We simply saw the dinosaur tracks. We saw, the algal materials, the mud cracks and that kind of thing, but we didn't actually see any fossils ourselves. But I might be able to find that reference handy. Hold on. I have a pile of stuff in front of me.
You're getting a lot of requests for field trips here.
Well, I love going field trips to the Navajo Sandstone. I mean, I actually, I don't ever think of anything original myself. And so I led a field trip years ago for Pertamina, the Indonesian National Oil Company. And I had them do the same thing as Dr. Hanlon did. I had them plotting wind direction in the Navajo, making a crude wind direction map, just like we did. So let me see. Dinosaur. There was a paper by Stokes in '91. That might have it in there. Of course, I have you on the line here. Fresh groundwater. Yeah, I'll have to look it up, but I think it was by Stokes or Gillian. That might be the other one that had identified those tree trunks. But they were not in the Lake Powell area. They were another, I think, more up towards Moab possibly. But you do see these, particularly the limestones. I didn't see the limestones as prevalent as you go farther to the west, although you do see interdune deposits there. But the limestones are best exposed, that I've seen anyway, in the eastern part, southeastern part of the state of Navajo, both at Lake Powell. Again, absolutely the best place to see them is Lake Powell, but now they're way high. But again, you can see them around the Moab area. I've seen them really well exposed there. And I always, again, speaking of field trips, I kind of do the same thing there. I take them to an outcrop and I say, we're in the Navajo. What's this? And they're saying, well, we got limestone. I go, how do you get limestone? And so, that leads to our discussion of the oasis deposits.
I think we'll have to follow up with you next spring to see if you can do a trip for the On the Rocks committee or something.
Okay, that'd be great.
Yeah.
I have a hard time saying no to Navajo stuff. So.
Yeah. Well, we'll keep it on the back burner, and I'll let Rob Dietrich know or Dan and see if they're interested in something like that. But that would be awesome. I think there's a lot of people